You are falling. There is no sound, there is no up or down, and there is nothing you can do to stop it. For most of human history, this was a fantasy, a monster dreamed up by physicists scribbling equations on chalkboards, something too strange to actually exist. Then, in 2019, humanity pointed a network of radio telescopes spanning the entire planet at a galaxy 55 million light years away and took a photograph of one. Not a drawing, not a simulation, a photograph. So, what actually happens if you fall into a black hole? Not the movie version, not the poetic version, the real, physical, mathematically brutal version. What does your body experience? What does your mind experience? And is there any way, even in theory, that you survive? Let's start with what a black hole actually is, because most people get this wrong immediately. A black hole is not a hole. There is no tunnel. There is no swirling drain sucking in nearby matter like a cosmic vacuum cleaner. A black hole is simply an object with so much mass, packed into so little space, that its gravity becomes inescapable. Not difficult to escape, not dangerous to escape, impossible. The boundary where escape becomes impossible has a name. It's called the event horizon. Think of it as a point of no return, an invisible line in space. Cross it, and every possible path forward, every direction you could ever move, leads only deeper in. Not because something is pulling you, because space itself is being warped so severely that outward stops existing as an option, the same way you can't walk toward yesterday. This idea comes from Albert Einstein's general relativity, published in 1915. But the first exact solution describing a black hole came just months later from a German physicist named Karl Schwarzschild. He was serving on the Russian front during World War I when he solved Einstein's equations for a single, non-rotating mass. Einstein himself doubted such an object could physically exist. He thought it was a mathematical curiosity, a strange trick of the equations that nature would never actually build. He was wrong. Decades later, physicist Roger Penrose proved mathematically that under the right conditions, black holes weren't just possible, they were inevitable. Any sufficiently massive dying star has no way to avoid collapsing into one. For that work, Penrose won the Nobel Prize in Physics in 2020. The universe, it turns out, builds these things constantly. So picture one, not a swirling purple cartoon vortex, a sphere of absolute blackness hanging in space, bending the light of every star behind it into a warped, smeared halo. That bending isn't decoration. It's the first clue about what's about to happen to you. Size matters enormously here, and it's measured in a very specific way. Every black hole has what's called a Schwarzschild radius, named after the same physicist who first solved the equations. It's the size the event horizon would be for a given amount of mass. Squeeze the entire Earth down to about the size of a marble, and it would become a black hole. Squeeze our sun down to roughly 6 kilometers across, about the size of a small city, and it would become one too. The physics doesn't care what the object used to be, only how much mass got packed into how little space. Most known black holes form the same way. A massive star, many times heavier than our sun, spends its life burning through fuel, holding itself up against the crushing weight of its own gravity through the outward pressure of nuclear fusion. When the fuel runs out, that outward pressure vanishes, and gravity wins completely. The star's core collapses in on itself, sometimes in less than a second, crushing an object larger than the Earth down to a single point. That collapse is what forms a stellar mass black hole. Larger, supermassive black holes, millions or billions of times heavier, are thought to grow over billions of years, feeding on gas, dust, and merging with other black holes at the centers of galaxies. Let's say you're in a spacecraft, falling feet first toward a black hole roughly the mass of our sun. Here's the first surprise. For a while, nothing dramatic happens at all. You'd feel normal, weightless, like any astronaut in freefall. No wind, no sound, no violent shaking. Space around you looks increasingly strange, but your body for now feels calm. This is one of the most counterintuitive facts about black holes. Falling into one doesn't feel like falling into fire. It feels like falling into silence. But gravity from a black hole isn't uniform. It's stronger at your feet, which are closer to the black hole, than at your head, which is slightly farther away. On Earth, this difference is so microscopically small, you'll never notice it in your lifetime. Near a black hole, that tiny difference becomes a monstrous force. This effect has a name, and it's one of the few pieces of black hole terminology that actually sounds as horrifying as it is: spaghettification. It's exactly what it sounds like. As you fall closer, the pull on your feet becomes so much stronger than the pull on your head that your body is stretched longer and longer, thinner and thinner, until you are pulled apart at the atomic level into a thin stream of particles, like human-shaped spaghetti being pulled through a strainer. For a black hole the mass of our sun, this happens brutally early, long before you even reach the event horizon. You'd be shredded apart while you were still millions of kilometers away. Physicist Kip Thorne, who won the Nobel Prize in 2017 for his work detecting gravitational waves and later served as the scientific consultant for the film Interstellar, has spent decades calculating exactly how this tidal stretching plays out for black holes of different sizes. And size, it turns out, changes everything. Think about what that stretching would actually feel like, moment to moment, if you somehow stayed conscious through it. First, your feet. A dull, growing ache, then a pull, then a pain unlike anything the human body was ever built to withstand, as the distance between your head and your feet is amplified by gravity itself, faster than any muscle or bone could resist. Your body isn't just being pulled. It's being pulled apart along its length while simultaneously being squeezed from the sides, compressed inward from every direction at once, the same way toothpaste is squeezed out of a tube. Physicists sometimes describe this dual effect, the stretching lengthwise and the squeezing sideways, as the true signature of a close encounter with strong gravity. Long before any of this becomes lethal, it would already be, by a wide margin, the most painful experience a human body could physically undergo. Here's the twist almost nobody expects. A small black hole is far more dangerous far sooner than a giant one. That seems backwards. Bigger should mean more destructive, right? But black hole physics doesn't work like ordinary intuition. The tidal force, the stretching force that spaghettifies you, gets weaker as the black hole gets bigger. A small black hole has extremely concentrated gravity that changes violently over short distances, which is exactly what shreds you. A supermassive black hole, like the one sitting at the center of our own galaxy, has its mass spread across a horizon so enormous that the difference in pull between your head and your feet, right at the boundary, might be almost nothing at all. Which means, in theory, if you fell feet first into a large enough supermassive black hole, you could cross the event horizon completely intact, alive, unstretched, unaware from the inside that anything unusual had even happened. The Event Horizon Telescope team confirmed the existence of exactly this kind of object in 2019 when they released the first image ever taken of a black hole's shadow at the center of a galaxy called M87. That black hole is roughly 6.5 billion times the mass of our sun. The image itself, a glowing orange ring surrounding a dark central shadow, wasn't a photograph in the ordinary sense. It was assembled by linking radio telescopes on multiple continents together, effectively turning the entire planet into a single lens large enough to resolve an object that far away. In 2022, the same collaboration released a second image, this time of Sagittarius A star, the supermassive black hole at the very center of our own Milky Way. You are right now orbiting roughly 26,000 light-years from an object exactly like the one that could, in theory, let you fall in without immediately tearing you apart. This is also roughly the scenario physicist Kip Thorne worked out for the black hole shown in Interstellar, a fictional giant named Gargantua. Thorne insisted the film's depiction be built from real equations rather than artistic guesswork, which is part of why the warped ring of light surrounding it and the extreme time dilation experienced by the characters near its horizon weren't just special effects. They were, as closely as a movie can manage, physically accurate visualizations of what general relativity actually predicts. So let's reconstruct that moment. You're not being shredded. You're simply falling, calmly, silently, towards something enormous. Your instruments would show your ship accelerating, but never violently. No turbulence, no jolt. Just a slow, steady, silent increase in speed as the black hole's warped geometry pulls you inward faster and faster. From your own point of view, Inside the spacecraft, you never actually see yourself cross the event horizon. There is no flash, no boundary line lighting up, no dramatic moment marked in space. You just keep falling, and looking back, the universe behind you starts to look increasingly bizarre. Light from stars behind you gets stretched and reddened. Light from stars ahead of you gets compressed and blue shifted. Eventually, the entire visible universe behind you appears to compress into a small, brilliant, warped point, while everything in front of you fades toward black. Meanwhile, something very different is happening from the outside. If a friend stayed behind in a safe orbit and watched you fall, they would never actually see you cross the horizon. Not because you don't cross it, because of how gravity affects the passage of time itself. This is one of the strangest confirmed predictions of general relativity. Gravity slows time. The stronger the gravity, the slower time moves, relative to someone far away. As you approach the event horizon, from your friend's perspective, you appear to move slower and slower. Your radio signals stretch out, arriving later and later at longer and longer intervals. Your image would appear to freeze, dimming and redshifting, fading like a photograph left in the sun, approaching the horizon forever without ever visibly, technically arriving. You'd become a kind of ghost, frozen at the edge for eternity, from their point of view. But from your point of view, none of that delay exists. You cross the horizon in what feels like an entirely ordinary amount of time. This isn't a trick or an illusion. It's one of the deepest and most well-tested predictions in all of physics, confirmed repeatedly through atomic clocks, satellite timing systems, and decades of astronomical observation. Two people, two completely different experiences of the same event, both correct, depending entirely on where you're standing. This kind of time distortion isn't unique to black holes. It happens in a much smaller way every single day, all around you. GPS satellites orbiting Earth experience slightly weaker gravity than we do on the surface, which means their onboard clocks run measurably faster than clocks down here. If engineers didn't correct for that tiny difference, the positioning errors on your phone's map would build up by several kilometers within a single day. Black holes simply take an effect that's already been tested and confirmed at a small scale, and push it to its most extreme possible expression. Near the event horizon, that same gravitational time distortion doesn't shift things by fractions of a second. It stretches a single moment out toward infinity from an outside observer's point of view. That has a strange consequence worth sitting with. In principle, if you watched a black hole form in real time from a safe distance, you would never actually see anything finish falling in. The collapsing star's surface would appear to slow, dim, and redden as it approached its own horizon, fading toward invisibility rather than visibly crossing a line. Everything that has ever fallen into every black hole in the observable universe is, from the outside, still technically arriving, an infinitely thin sliver of time away from crossing, forever frozen at the threshold, even while, from its own perspective, it crossed long ago and kept going. So now you've crossed the horizon. What happens next? This is where honest science has to admit something uncomfortable. Nobody actually knows for certain. Once you're inside, general relativity predicts that all paths, every possible direction you could travel, lead inevitably toward a single point at the center, called the singularity. It's the spot where, according to the math, gravity becomes infinite, space and time break down entirely, and the equations of physics simply stop working. Not become difficult. Stop working. Give nonsensical answers. Divide by zero. This is the point where general relativity, the same theory that predicted event horizons, spaghettification, and time dilation, and got every single one of them right, essentially throws up its hands and admits it has no idea what's actually there. Most physicists don't think infinite density is physically real. They think it's a sign that we're missing something, that a full theory combining general relativity with quantum mechanics, something physicists call a theory of quantum gravity, would replace that infinite point with something else entirely. Nobody has that theory yet. It remains one of the biggest open problems in all of physics. This is exactly the kind of breakdown Roger Penrose proved was unavoidable back in the 1960s, using nothing but pure mathematics. Before his work, some physicists suspected the singularity might just be an artifact, a mathematical mistake caused by assuming a perfectly symmetrical, non-rotating collapse, something real stars, spinning and irregular, would never actually do. Penrose showed that assumption didn't matter. Using a method involving what he called trapped surfaces, regions of space where every possible outward-pointing beam of light is forced to bend back inward, he proved that once such a surface forms, a singularity of some kind becomes mathematically unavoidable, regardless of how messy, lopsided, or spinning the collapsing object actually is. That proof, decades later, earned him the Nobel Prize in Physics, shared in 2020 with the astronomers who discovered the supermassive black hole at the center of our own galaxy. What we do know is this: from the moment you cross the event horizon, the singularity isn't a place you're traveling toward, the way you'd walk toward a wall. It's your future, literally. Inside a black hole, the roles of space and time swap. Outward and inward stop being directions you can choose between, the way north and south are directions on Earth. Instead, toward the singularity becomes something more like later, the same unavoidable way that next Tuesday is unavoidable. You can't refuse to move toward it any more than you can refuse to move forward in time. There is no engine powerful enough to reverse it. No amount of thrust, no clever piloting changes your outcome, said E, because you're no longer choosing a direction in space. You're choosing when. For a small black hole, this final stretch to the singularity happens in a fraction of a second, and by then, you've already been spaghettified long before reaching this point anyway. But for a large supermassive black hole, this last stage can take hours. You could, in theory, survive intact for a genuinely significant amount of time, floating inside the event horizon of something like the black hole at the center of our galaxy, before tidal forces finally catch up and end you. And here's a detail that tends to unsettle people the most. During that time, you wouldn't necessarily know you'd crossed the horizon at all. There's no wall, no sign, no dramatic shift in sensation the instant you pass it. You would simply be falling inside a black hole and not know it until the moment the math finally, inescapably, catches up with you. Now, there's one more piece to this story, and it comes from theoretical physicist Stephen Hawking. In 1974, Hawking made one of the most important and unexpected discoveries in the entire history of black hole physics. Black holes, he showed, are not perfectly permanently black. Through a quantum effect happening right at the edge of the event horizon, they very, very slowly emit radiation and lose mass over unimaginably long timescales. This process is now called Hawking radiation. Given enough time, trillions upon trillions of years, far longer than the current age of the universe, a black hole would theoretically evaporate away entirely. This discovery matters for our story because it raises one of the strangest open questions in physics. What happens to all the information about you, your atoms, your structure, everything that made you, once the black hole that swallowed you eventually evaporates away to nothing? Physics has a rule that information can't simply be destroyed. But if you fell in and the black hole eventually vanishes, where did you go? This is known as the black hole information paradox. And physicists, including Hawking himself before his death in 2018, spent decades wrestling with it. It remains, even now, unresolved. The radiation Hawking predicted comes from a quantum effect happening right at the edge, at the event horizon itself. Empty space, according to quantum mechanics, isn't actually empty. It constantly produces pairs of particles that flicker in and out of existence, so briefly and so faintly that under normal circumstances, they never affect anything at all. But right at a black hole's horizon, that pattern can be interrupted. One particle of a pair can fall in, while the other escapes outward, carrying a tiny sliver of energy away with it. Do this often enough, over long enough stretches of time, and the black hole very slowly loses mass, radiating itself away, particle by particle, until, in a timescale almost impossible to picture, nothing is left at all. For a black hole the mass of our sun, that process would take roughly 10 to the power of 67 years, a number so much larger than the current age of the universe that the comparison barely means anything at all. So let's step back and put the whole picture together, the way you'd actually experience it. You fall. For a long while, it feels calm, ordinary, almost peaceful. If your black hole is small, that calm ends violently and early, torn apart by spaghettification long before you even reach the horizon. If your black hole is large enough, you cross that boundary without even noticing, still intact, still yourself, while a friend watching from a distance sees you fade into a frozen, reddened ghost at the edge, forever. Inside, your future stops being a place and becomes a direction in time. An unavoidable countdown toward a boundary where our best equations simply stop making sense. And somewhere out there, an unfathomable stretch of time later, the black hole that swallowed you slowly radiates away into nothing, leaving physicists still arguing about where exactly you went. It's worth sitting with why this matters, beyond the raw spectacle of it. Black holes force our best theory of gravity to confront its own limits. They are, in a very real sense, laboratories, the universe built for testing the edge of human knowledge, sitting quietly in the centers of galaxies, invisible except for the way they bend light and warp time around them. Every field of physics has a place where its equations stop working, a boundary where confident predictions dissolve into open questions. For most of science, that boundary is tucked away, hidden inside particle accelerators or buried in conditions no human will ever personally encounter. Black holes are unusual because that boundary is, in principle, something you could physically travel to. You could point a spacecraft at one, cross into a region where our best theory admits it doesn't know what happens next, and simply keep going. Few places in the universe let you walk directly up to the edge of human knowledge and step across it. And that's the strange thing about studying something you can never return from. Every prediction we have about the inside of a black hole is built entirely on math extrapolated from the outside. Nobody has ever come back to confirm it. Maybe nobody ever will. And yet, through Schwarzschild's equations from a battlefield in 1915, through Penrose's proofs, through Hawking's radiation, through a literal photograph taken by a telescope the size of Earth, humanity has managed to reconstruct, with startling confidence, the fate of anything that crosses that boundary. You started this falling into silence, with nothing you could do to stop it. And in a strange way, that's exactly where your ordinary life already stands. You are, right now, moving forward through time at a fixed, unstoppable rate, toward a future you cannot refuse, shaped by forces far larger than yourself that you'll never fully see the edges of. You don't notice it the way you'd notice a wall or a wind, because it's the medium you exist inside, not an obstacle you run into. A black hole simply makes that ordinary, invisible fact impossible to ignore by dragging the future so close and so unavoidably that it stops feeling abstract. A black hole doesn't just show you what happens if you fall in. It shows you, in the most extreme terms physics has ever produced, what it means to have no choice but to keep moving forward.